Today, I start about one important topics related to measure theory. Okay, we now discuss about some that means variation, positive variation, negative variation, total variation. We discuss about these topics. We also in previous class we also discuss Hahn decomposition and Hahn decomposition theorem and related topics. Okay, so today I start about here. Here we start about this definition of positive variation, negative variation, and total variation. These topics. Okay, so we write this definition now. Okay, let x this a mu be a signed measure space. Okay, be a signed measure space and let let pn be a Hahn decomposition for of x for mu. Let pa be a Hahn decomposition of x for mu. Okay, define set function okay, mu plus and mu minus and mod mu. Okay, here a the script a to 0 plus infinity closed by okay for t belongs to the script a mu plus e equal to mu of p intersection e greater than equal to 0 and mu minus e of okay here mu of in intersection e here difference greater than equal to 0 and modulus of okay mu e equal to here mu of p intersection e okay difference mu of n intersection e okay this one greater than equal to 0 equal to mu plus e plus mu minus e. Okay, I understand. Then what happened? Then we erase our portion and going to further discussion of that. Okay, then first one, the set function mu plus the set function mu plus is called positive variation for mu. Is called positive variation for mu. Okay, second okay the set function mu minus is called negative variation for mu. Okay, and number 3 the set function modulus of mu is called total variation for mu. Total variation for mu. Okay. Then what observation we see now? Okay. We erase our portion and going to further discussion of that. We write here observation. Okay. We write here observation. First one, mu plus and mu minus are measured. Mu plus and mu minus are measured on XA. Okay. 2. Modulus of mu be a measure on X IA. Okay. And again we talk about it, mu plus n equal to mu of P intersection n. Okay, this equal to 0, mu phi equal to 0, and 4 here, mu minus of P equal to mu of P intersection n equal to minus here. Okay, minus mu of P intersection n equal to 0. Okay, then what happened? Then obviously we see about that. Okay, we now erase that portion and going to further discussion of that. So the set function mu plus be positive variation for mu, and the set function mu minus is called negative variation for mu, and the set function mod of mu is called total variation for mu. Okay, now we erase that portion and going to discussion about that mutually singular measure. Okay, that mutually singular measure. Okay, let mu1 and mu2 be two measures on a measure space. Let mu1 and mu2 be two measure on a measurable space, on a measurable space X gift A. Then we say that mu1 and mu2 are mutually singular, if there exists two measurable set, sets, okay, A and P, such that what, X equal to A union B and A intersection B equal to phi, and mu1 of A equal to 0 and mu2 of B equal to 0. Okay, so what happened? This one, mu1 and mu2 be two measure on a measurable space X A skipped A, then we say that mu1 and mu2 are mutually singular if there exists two measurable set A and B such that X equal to A union B and A intersection B equal to phi and mu1 of A equal to 0 and mu2 of B equal to 0. Okay, now we write about here. Okay, mu1 and mu2, mu1 and mu2 are mutually singular, are mutually singular if there exists a measurable sets such that mu1 of E equal to 0 and mu2 of X difference E equal to 0. Okay, so we talk about that mu plus and mu minus are mutually singular measure. Okay, again we talk about that mu plus and mu minus. Okay, mu plus, mu minus, we also discuss here mu plus and mu minus all are mutually singular measure. Okay, that means mu plus equal to p in mu of p intersection E, mu plus E, and mu minus E equal to n intersection E. Okay, minus n intersection E. Then obviously mu plus and mu that means minus are mutually singular measure when, because these two intersection, that means P intersection E and N intersection E, if we construct, that means this E is not here. Okay, then mu plus and mu minus, because the mu minus are mutually singular. Okay, so that means this E is here. We talk about that portion. Okay, if mu1 and mu2 are mutually singular, then mu1 and mu2 are perpendicular. Okay, we write it first, then we discuss about that. We not write it now. So mu1 and mu2 are perpendicular. Okay, perpendicular. Now we talk about mutually singular sign measure. Okay, so today we discuss this type of mutually singular measure. Okay, and obviously positive variation and negative variation and total variation. Now we erase that portion and going to discussion about mutually singular sign measure. Okay, so we erase that portion and going to discussion about that. Mutually singular sign measure. Okay, now we write it here. Let mu and this lambda, gamma, mu and gamma, oh sorry, not this lambda, mu and gamma be two sign measure. Okay, on a measure space, on a measure space x the script a. Okay, then we say here this mu and comma are mutually singular if there exists two measurable set, if there exist two measurable sets, okay, a and b a and b such that x equal to a union b and a intersection b equal to phi, and mu mod of mu x, okay, a equal to 0 and mod of comma b equal to 0. Okay, this one is mutually this one is mutually singular sign measure. Okay, that means in mutually singular measure just mu1 a is 0, and here mu mod of mu means this total variation for mu, okay, and total variation for gamma of beta is 0. Okay, so what happened here? Here we discuss some example about that. Okay, we write it example here. Example here, we write it now. Let x equal to 0 1 and let this one closed 0 1 m intersection closed 0 1 mu be a Leibniz measure, be a Leibniz measurable set, Leibniz measurable space. Okay, then define for a belongs to the script a. Okay, mu half a equal to 1. Okay, if half belongs to a and 0 if half does not belongs to a. Okay, then what happened? Then mu half a measure on x a. Okay, then mu half is a measure on x a, and obviously mu p equal to 0. Okay, mu of half equal to 0, and here mu half n equal to 0. Okay, then what happened? Then we talk about that. Okay, take here mu and mu half are measured in here, this one mu and mu half. Okay, so we write it now in our portion. We erase that definition portion. Okay, here mu and mu half, here mu and mu half, here mu and mu half are measured on this x script a. Okay, and now second option, this one. Okay, take e equal to this half and n equal to 0 1 close difference this half. Okay, then mu p equal to 0 and mu n equal to what happened, sorry, mu half n equal to 0. Okay, then what happened, hence hence mu perpendicular mu half. Okay, that means mu is perpendicular to mu half. Okay, next we erase that portion and going to be another another example of that. Okay, we write it now. Same let x equal to 0 1 close. Okay, and and here 0 1 closed and m intersection 0 1 closed intersection here mu be a Leibniz measurable space, be a Leibniz measurable space. Okay, then define for a belongs to this script a and mu, sorry, not mu, then then gamma a equal to what, gamma a equal to cardinality of a or number of elements in a, number of elements in a. Okay, then what happened, then this one first we write about that mu and gamma be measured on this x, this 50. Okay, number 2, take a equal to 5 and p equal to x. Okay, hence this comma a equal to 0, what mu b equal to 1, not equal to 0. Okay, so we'll talk about that. Therefore, okay, therefore gamma and therefore mu and gamma are not mutually singular, not mutually singular. Okay, not mutually singular. So we also discuss about that mutually singular. Okay, mutually singular measure and which one is mutually singular and which one is not. Okay, so we also discuss here, then we also then going to further discussion of that. Okay, we also further discussion of that, but today I not continue this. Today I just discuss this one, positive variation, negative variation, total variation. Okay, and then obviously mu plus and mu minus are measures, and obviously total variation, that means are measured on x-axis. Okay, we discuss about that in observation. And mu plus n equal to 0 and mu minus p equal to, okay, 0. So in this way we talk about that mu plus and mu minus are mutually singular. Okay, then mutually singular measure we also discuss about that. Some measure, two measure is mutually singular if there exists two measurable set x equal to a union b and a intersection b equal to phi, and mu 1 a equal to 0 and mu 2 b equal to 0. Then mu 1 and mu 2 are mutually singular if there exists measurable set such that mu 1 e equal to 0 and mu 2 x difference e equal to 0. Okay, then mu plus and mu minus are mutually singular measure. If mu1 and mu2 are mutually singular, then mu1 and mu2 are perpendicular. Okay. Then we're going to discussion about mutually singular sign measure. Okay. Let mu and gamma be two sign measure on a measure space X descript A. We say that mu and gamma are mutually singular if there exists two measurable set A, B such that x equal to A union B, A intersection B equal to phi, and total variation of A, total variation for mu of A is 0 and total variation for gamma of B equal to 0. There exists two measurable sets. Then we find some, we also give one example related to mutually singular sign measure space. So today I stop here. Okay, if you get this type of video, please subscribe my channel, and if you then like or if you that means getting this video and have some improve in your that means study, then please encourage me, gives like. Okay, please gives like. And if any suggestions, any questions, any comments, write it in comment box. So please subscribe my channel. Today I stop here.